Now we will see low pass filter and high pass filter with sinusoidal input. Okay. So, generally for the linear circuit, if you apply sine wave as the input, the wave shaping will not be done. What is the meaning of this one? If you apply sine signal as the input, whatever the output you are getting, that output shape will not be different from the input shape. Okay, actually wave shaping means output signal shape should be different from the input signal shape. But for the linear circuits, if you apply the sinusoidal signal, output is also sinusoidal signal only. There is no change in the shape of the signal, but there may be a changes in the amplitude levels, there may be a changes in the phase. Okay. Now this topic is about that particular thing only. Okay. So we will take the low pass filter circuit here. So we know low pass filter is nothing but we will be having resistor and then capacitor. This is our low pass filter. Here we have to apply input signal and here we need to get output signal. And high pass filter means we know capacitor, resistor are to be connected like this. Here we have to take the output across the resistor and here we have to apply the input for this particular combination. Okay. Then we are going to analyze now. If you apply the sinusoidal signal, what is the effect? Okay. As I said earlier, wave shaping will not be done. Okay. So, for the low pass filter or for the high pass filter, both are linear elements only. Okay. R and C linear elements only. So, both circuits are linear circuits only. So, linear circuit cannot able to provide the wave shaping process for the sinusoidal input. So, output is also sinusoidal. So, you may have the changes in the amplitude and phase. Okay. So, to have the transfer function in these two cases, we are going to apply Laplace transform. So, we are going to draw the circuit again by having by considering the impedances in the Z transform. Okay. Sorry, in the Laplace transform or in the Fourier transform. Okay. So, in the Fourier transform, this Zc, the impedance offered by the capacitor Zc is actually given by 1 by j omega c. Here I am going to explain how we got this one. We know about capacitor current, current is equal to C into dV by dt. So, actually this voltage and current are changing with respect to time. Okay. So, I of t is equal to C into dV of t by dt. So, like this I have written. I am assuming that current and voltage are changing with respect to time. So, V is a function of time, that is why I have written V of t, and I is the function of time, that is why I have written I of t. Now, apply Fourier transform for this particular equation, Fourier transform. I of t means I of omega, like for x of t, x of omega is the Fourier transform. We can tell this I of t is having the Fourier transform I of omega, C is the constant, and V of t is having the Fourier transform V of omega. D by dt means what? Differentiation in the time domain leads to multiplication of the variable in the frequency domain. We know the property about the Fourier transform. So, d by dt means j omega we have to take, and V of t Fourier transform is V of omega. I need impedance, that means voltage by current. So, if you write equation for V of omega by I of omega, and if you consider that is a Zc, you will be having 1 by j omega c. So, in this manner we got Zc. But now I am going to use the transfer function definition as the Laplace transform of the output by Laplace transform of the input. Okay. So, that I need to write this one in the Laplace transform, that means in the S domain. So, we know S is equal to sigma plus j omega. If you consider sigma is 0, j omega itself is Sc, that means 1 by Sc. Okay. So, Zc can be taken as 1 by j omega c or 1 by Sc. Now, we are going to redraw the diagram. Okay. By considering this one, R will be R only, no changes in that one. So, R will be R only. So, then this capacitor impedance we have to take as Cs, 1 by Cs. V naught of t will become V naught of S, Vi of t will become Vi of S, R will be R only. So, now you can apply voltage dividing rule to get the output voltage. Okay. R and 1 by Cs both are in series. So, the supply voltage VA of S is divided in between these two. So, to have the voltage across this particular capacitance, we can able to apply voltage dividing rule. So, the voltage across the capacitor itself we can able to consider as V naught of S, that is equal to supply voltage VA of S multiplied with where we are finding that impedance by, that means 1 by Cs by 1 by Cs plus R. This is what we can able to write. Okay. Now, bring this VA of S to the left side and replace S is equal to j omega again, then what you will get? V naught of j omega by Vi of j omega is equal to, here 1 by Cs by 1 by Cs plus R is there. So, in the denominator you can take LCM, you will get Cs as LCM, numerator Cs, denominator Cs will be cancelled. So, finally you are going to get 1 by 1 plus RC S, S means j omega. Okay. And j omega means what? 2 pi f. So, 1 by 1 plus j omega means 2 pi f into RC. This is what we got now. Okay. So, this V naught of j omega by Vi of j omega can be considered as a gain now, output by input, that is called gain, and that is a function of frequency actually. Okay, that is a function of frequency. If you see this particular equation here, frequency is there. With respect to frequency, that gain is changing. This is very important conclusion here. Okay, frequency is the function of this gain is the function of frequency. Okay, that is what we have to identify. Now, I am stopping the derivation here. Now, I am coming to high pass filter. Why I am dealing these two simultaneously means the procedure is same. So, you can able to understand the concept very easily when you compare and study. Okay. For the sinusoidal input, now we are going to analyze both low pass filter and high pass filter. I have got the gain equation now in case of the low pass filter. Similarly, I am going to get gain equation in case of the high pass filter. Okay. So, same procedure, I am going to modify this particular diagram in the S domain. So, capacitor with 1 by Cs is the impedance, and resistor R, because resistor is independent of frequency, it will not be affected, and here V naught of S and it is Vi of S. From this one only I got this one. Okay. Then by applying the voltage dividing rule, we can get V naught of S is equal to output total voltage is Va of S multiplied with the impedance where we are finding the output voltage, that is R, by total impedance, that is R plus 1 by Cs, like this I can write. Okay. Now, you can take R common in the denominator, that R can be cancelled with the numerator R. So, in the numerator you are leaving with Va of S only by 1 plus 1 by RCS. So, like this we can write. Bring this Va of S to the left side, you are getting the transfer function, that is equal to V naught of S by Va of S, and this is equal to, you are leaving with 1 by 1 plus 1 by RCS. Now, write in the frequency domain part, that means S is equal to j omega you can able to consider. So, A is equal to, this is itself is gain as I said earlier. So, 1 by 1 plus 1 by RC, S is equal to j, omega means 2 pi f, and we know 1 by j is nothing but minus j. Okay, 1 by j is nothing but minus j. Okay. How did we get this one? Minus 1 means j square, that means plus 1 means j power 4. So, here we can write 1 means j power 4 by j, that is j cube, that is j square into j square is minus j. So, like this we can tell 1 by j means minus j, remember that one. So, I am replacing that one. So, 1 by 1 by j means minus j by 2 pi f RC. Similar kind of equation we got in case of the low pass filter also, you can observe that one. A is equal to 1 by 1 plus j 2 pi f RC, and in the high pass filter we got A is equal to 1 by 1 minus j by 2 pi f RC. So, here also gain is changing with respect to frequency, because here frequency f term is there, and in the low pass filter also gain is changing with respect to frequency. Okay. So, procedure is same, that is why I am dealing these two operations at a time. Okay. Do not have any confusion here, okay. You can able to understand very clearly. And at this moment, as I said earlier, I have understood that gain is the function of the frequency. So, you can represent like A of f, and here also you can able to represent with A of f. So, I am writing again here this equation, A of f is equal to 1 by 1 plus j 2 pi f r c. Okay. So, as the gain is the function of frequency, I am using A of f. For example, x is the signal which is the function of time, we are representing like x of t. Here gain A is the function of f, that is why I am representing with A of f, and in the high pass filter also same case. Okay. So, now what next? What next in the sense, if you see the definition of the low pass filter, what is the definition I have given? It is the filter means frequency selective circuit. Actually filter is the frequency selective circuit. It is selecting only certain frequencies, those frequencies are sent through the filter and remaining frequencies are rejected by the filter. Okay. Frequency selective circuit, filter is the frequency selective circuit. Low pass filter is nothing but it allows low frequencies, rejects high frequencies. High pass filter means it allows high frequencies and rejects low frequencies. Rejects low frequencies means what is the criteria for that one? Okay, what frequencies can be considered as the low frequencies in case of the high pass filter, or what frequencies can be considered as the high frequencies to allow by the high pass filter. And in case of the low pass filter also same thing, what frequencies are to be considered as the low frequencies to pass through the low pass filter, what frequencies we have to consider as the high frequencies to pass through the high pass filter, what is the criteria for that one? Okay. What is the limitation for that one? What can be considered as a low frequency and what can be considered as a high frequency? That is given by cutoff frequencies. Okay. One cutoff frequency is there in case of the low pass filter, and using that one we can tell these are the frequencies which are low frequencies, these are the frequencies, these are high frequencies. Like that we can able to differentiate the frequencies using cutoff frequencies. Okay. And in case of the low pass filter, we are having the higher cutoff frequency represented with the FH. In case of high pass filter, we have higher cutoff, this lower cutoff frequency FL. Okay. Low pass filter higher cutoff frequency is available FH, and high pass filter lower cutoff frequency is there FL. And in these two cases both formulas are same, that is FH is equal to 1 by 2 pi RC and FL is also equal to 1 by 2 pi RC, formulas are same. Okay. About RC you are going to understand in a better way when we apply step input. Okay. For the time being you try to remember these formulas. So, FH is given by 1 by 2 pi RC and FL is equal to 1 by 2 pi RC, and FH is available for the low pass filter, this is a higher cutoff frequency, and FL is called lower cutoff frequency, this is available for high pass filter. So, the frequencies which are below FH are taken as the low frequencies. Okay. Next, the frequencies which are beyond FH are called higher frequencies. Similarly, in case of the high pass filter also. Okay. Now, we are going to draw the graph in between gain versus frequency. Before going to see that one, we need to get a magnitude. Okay. Magnitude of these two things. So, if you substitute this particular FH value in case of this A equation, I am going to get like this 1 by or A of f, if you consider it is A of f is equal to 1 by 1 plus j f. 2 pi RC is there, actually FH is equal to 1 by 2 pi RC, since we have 2 pi RC I need to write 1 by FH. Okay. So, I can modify A of f equation like this, 1 by 1 plus j f by FH I got now. Now, in case of the high pass filter, similarly we can substitute FL is equal to, wherever 1 by 2 pi RC is there we can write a FL. So, A of f in case of the high pass filter is given by 1 by 1 minus j FL by f. So, like this we can write. Okay. So, I am going to the next slide now. whatever the equations I got previously, those equations I am writing again here. So, A of f is equal to, we got now 1 by 1 plus j f by fh we got, and in case of the high pass filter we got A of f is equal to 1 by 1 minus j, it is fl by f we got. And what is fh, what is fl, we know already, that is 1 by 2 pi rc. Okay, magnitude wise those two are same. Now, what is the magnitude of this particular total gain function? If you take the magnitude of A of f, you will get a numerator is 1 only and denominator is in the form of the complex form a plus jb. So, the magnitude is given by square root of a square plus b square. So, I am getting square root of 1 plus f by fh square. And if you take here the magnitude A of f is equal to 1 by square root of 1 plus fl by f square. So, like this we will get. Okay. And phase also you can able to consider, here I am taking phase, that is also changing with respect to frequency. Numerator phase is 0, denominator phase is given by tan inverse of f by fh by 1. So, that is tan inverse of f by fh, and numerator phase minus denominator phase, if you take minus tan inverse of f by fh you will get, and here also phase theta of f is equal to what you will get here, numerator phase is 0 minus denominator phase is tan inverse of minus of fl by f. So, like this you will get. Okay, you can modify that one. Here we are going to deal with the gain, that is why I will concentrate on gain versus frequency. So, what is the frequency response means, gain versus frequency only. We need to draw the plot in between gain and frequency. Okay. And this gain you can take in dB also. In the experiments in the lab, you are going to draw the plots finally gain in dB versus frequency, gain in dB versus frequency for both the low pass filter and high pass filter. Now, without taking in dB, by using this particular expression only I am going to draw. Okay. So, see here carefully, on x axis we have to take the frequency, on y axis I am taking here gain, magnitude of the gain. So, in this case also same thing, frequency, and on y axis I am taking the magnitude of the gain, like this I am taking. Okay. So, now we will analyze at different frequencies what is happening. At f is equal to 0, at f is equal to 0, you see this equation. Okay. At f is equal to 0, what is happening to the gain? F is equal to 0 means 0 by fh is 0. Okay. F is equal to 0, I am taking here f is equal to 0, I am substituting. So, 0 by fh is 0, 0 square is 0, 1 plus 0 is 1, root 1 is 1, 1 by 1 is 1. That means gain you are getting 1, gain you are getting 1 at f is equal to 0. At f is equal to 0, you are getting gain is equal to 1 you are getting. That means 0 frequency is allowed, gain is available means that particular frequency component is passing through the circuit, passing through the filter. Low pass filter means what? It allows low frequencies. Okay. So, that we can able to tell like that. At f is equal to 0, what is happening means this is what is happening. Okay. So, at f is equal to 0, we are having the gain. Now, you consider very high frequency. Okay, very high frequency, approximately infinity. So, if you take f is equal to infinity, simply if you substitute here f is equal to infinity, what is happening? Denominator is becoming infinity, 1 by infinity means gain will become 0. Okay. So, gain will become 0. If you draw the plot here, in between 0 frequency to very large frequency, the gain is decreasing like this. Simply we can tell here gain is in the denominator, that is enough to tell the frequency is in the denominator, that is enough to tell gain is inversely proportional to frequency. So, as frequency is increasing, gain is decreasing, like this we will get the plot. Now, coming to high pass filter. Okay. So, again we have to see the relationship between the gain and frequency. Here gain frequency term is there in the denominator, but it is fl by f. So, if you take LCM, you can able to observe the exactly frequency term is there in the numerator only. Okay. So, the numerator part is dominating the denominator part. So, that we can able to tell here as frequency is increasing, the gain value is increasing, you can check by taking two values 0 and infinity. So, if you substitute here f is equal to 0, what will happen? Something by 0 is infinity. Okay. So, denominator is becoming infinity, something by infinity means 0. So, you are getting 0 gain at frequency is equal to 0. Gain is 0 means 0 frequency content is not passed through the filter. So, high pass filter is not allowing the DC content, it is allowing only high frequency. DC means 0 frequency, that is why DC value is not passing through the high pass filter. Now, if you consider f is equal to infinity now, at f is equal to infinity what will happen? Something by infinity is 0, 0 plus 1 is 1, 1 by 1 is 1, that means gain is 1. At very high frequency you are getting gain is 1, okay. Here also gain is 1. So, you will get the plot is like this, okay. So, high frequencies are allowed by the circuit in case of the high pass filter and low frequencies are rejected, high frequencies, low frequencies. Here in case of the low pass filter, low frequencies are allowed as gain is maximum and high frequencies are rejected, okay. So, it is not enough, we have to include here cutoff frequency, okay. So, we know fh is equal to 1 by 2 pi RC. fh is constant, listen this one very carefully, fh is constant. Here FL is equal to 1 by 2 pi RC. For the given circuit, R and C values are constants. So, FL value is also constant if you substitute R and C values. So, FH and FL both are constant values, okay, both are constants only. But F is a variable. If you observe on x axis we have taken F, F is the variable, okay, remember that one. F is the variable, FH and FL are constants. Variable means it is having so many values, constant means only one value. So, FH is actually one of the values of F. Similarly, FL is one of the values of F. What is that value? 1 by 2 pi RC. If you calculate, you will get one number. So, FH may be here for example, okay, FH may be here. In this case, FL may be here, whatever it may be. Simply I am taking here. This is the FH value, this is FL value. If you calculate, somewhere you will get like a FH and FL like this. Okay. So, what is the gain particularly at f is equal to fh? What is the gain particularly at f is equal to fl? If you observe very carefully, if you substitute here in place of f, if you substitute fh, what will happen? fh by fh is 1, 1 square is 1, 1 plus 1 is 2, root 2 is there, 1 by root 2 you are getting. 1 by root 2 value is equal to 0.707. So, when f is equal to fh exactly, then the gain will become 0.707. Now, coming to high pass filter, at f is equal to fl you calculate, at f is equal to fl, if you substitute f is equal to fl, the gain will become again same value, that is 1 by root 2, that means 0.707. So, this is 1. So, at f is equal to fl, if you calculate the gain you will get 0.707, that is actually 1 by root 2. Okay. So, this thing we can able to use it for the definition of the FL and FH. Okay. Previously I did not define them, simply I have given those are the higher cutoff frequency and lower cutoff frequencies, and the formula is given by 1 by 2 pi RC. Now, with this concept I am going to define the higher cutoff frequency and lower cutoff frequency. So, see carefully, in case of the low pass filter, now I am going to define the higher cutoff frequency. Higher cutoff frequency FH is the frequency, okay, is the frequency at which the gain is given by 70.7% of the maximum gain. What is the maximum gain? 1. So, out of 1, 70.7% of the maximum gain is available for the circuit at this particular frequency. Similarly, in case of the low pass filter also, high pass filter also, the lower cutoff frequency FL is defined as the frequency at which the gain is the 70.7%. We can tell in percentages, or we can tell 1 by root 2 times of the maximum gain. Okay, you can tell 1 by root 2 times, or you can tell 0.707 times, or you can tell 70.7% of 1, or maximum gain. Maximum gain. So, this thing you need to remember. Using this particular concept, you can able to define FH value and FL value. Okay. So, with this we have completed the low pass filter and high pass filter circuit operations with sinusoidal input. Okay. One thing you need to remember, that frequency response plots we are drawing in this particular case, For the low pass filter and for the high pass filter, we are drawing the frequency response plots by providing the sine signal as the input. Okay, that is one thing where we are getting the FH concept and FL concept. And one more very important point is wave shaping is not occurred. Wave shaping is not occurred. Okay, when sine or cos inputs given for LPF or HPS, particularly for the linear circuit. For the linear circuit, if you apply sine or cos signals as the input, wave shaping will not be done. That means output is again sinusoidal signal only. That is what we have to consider. Okay.